Last episode we sized the deployment and found the weights are the fixed cost, 14 gigs for a 7 billion model in 16-bit. This episode we attack that fixed cost directly. Quantization, round the model's numbers to fewer bits so it is smaller and faster. The whole art is one question. What is the lowest precision the model still survives? Quantization is rounding with a scale. Take a weight, divide by a scale factor, round to a small integer or a low bit float, and remember the scale so you can undo it approximately later. 8 bits, 4 bits, smaller weights, less to stream from memory, faster decode. The cost is a little error every time you round. The question is whether that error matters. 2 ways to do it. After training, post-training quantization PTQ, you take a finished model and show it a few hundred example sentences, called a calibration set, just so it can measure how big its numbers usually get and pick good scales. Minutes to hours no retraining, that is the default, or quantization aware training, quote, where you simulate the rounding during fine-tuning, so the model learns to tolerate it. One practical note, run quart as a short fine-tune at a much lower learning rate, 10 to 100 times smaller than the original. With a warm-up, the rounding noise makes big steps unstable. Quart wins at the very lowest bit widths, but it costs a real training run. And either way, you do not trust the bits, you measure the accuracy after. Now the clever part, not all weights matter equally. A tiny 1% slice of weight channels carries most of the behavior. The salient ones, the ones tied to the biggest activations. AWQ, Activation Aware Weight Quantization, scales those to protect them and rounds the rest hard. It is fast and usually beats the older GPTQ, which instead compensates rounding error layer by layer using curvature information. And SmoothQuant solves a different problem, wild activation outliers, by mathematically shifting them into the weights, so both sides quantize cleanly to 8-bit. Which one do you pick? 2 questions. First, batch size. At low batch, decode is weight loading bound, so quantize weights only. 4-bit weights, 16-bit activations, AWQ shines. At high batch, the matmul itself is the cost, so go weight and activation 8-bit, SmoothQuant or FP8, and run the math in low precision on the tensor cores. Second, your hardware. On Hopper or Blackwell, NVIDIA's advice is blunt. Try FP8 first, best speed and accuracy together. Fall back to INT8 SmoothQuant, then INT4 AWQ, only if accuracy demands it. Let me show you the real NVIDIA quantization path. TensorRT model optimizer, a calibration loop, and the measurement that actually decides it. Left the code, right the terminal, including the accuracy numbers. Pick a recipe. Model opt ships them as configs, FP8 default, INT8 SmoothQuant, INT4 AWQ. We start with FP8 because that is NVIDIA's first try recommendation on Hopper and Blackwell. The calibration loop. We pass a forward function that runs about 500 sample batches through the model. That is the calibration set fitting the scales. Then mtq.quantize wraps the model, inserts the quantizers and calibrates. No retraining, just a few hundred forward passes. Now the part the bit width cannot tell you, measure. We run perplexity and an MMLU slice on the FP8 model and compare to BF16. Watch the terminal. BF16 perplexity 5.68, FP8 5.71. MMLU drops from 68.2 to 68.0, less than 1%. FP8 survives, ship it. If it had not, the next line shows the INT8 SmoothQuant and INT4 AWQ fallbacks, each remeasured. So round the weights down, calibrate on a few hundred samples, and measure FP8 first, then fall back only if accuracy demands. We have now shrunk the model to fit and fly, but a small, fast model still has to be served, batched, scheduled, kept saturated under real traffic. That is the next stage, paged attention, continuous batching, and the serving engines. vLLM, TensorRT-LLM, Triton, and NIM. Thanks for watching. Thanks for watching. Like and subscribe for more videos like this, and I'll see you in the next one.